Good morning. This is the second question and answer video I'm making in response to a question that I got from some of the audience of this course. And the question was about the stochastic calculus. We spent some time in defining the Ito stochastic calculus as opposed to other forms of calculus. For instance, one that is often referred to is the Stratonovich stochastic calculus. The reason we focused on the Ito stochastic calculus was that it was very simple to turn into a practical rule for solving the overdamped Langevin equation, because it amounted to have everything. You have a time t on the right hand side of the equation, and from that determine the position at time t plus 1. So in this sense, the Ito calculus is explicitly Markovian, and therefore you can simply, the Ito rule for differential equations is basically an iterative procedure through which you evolve the entire system. The Stratonovich calculus evaluates the stochastic force not at the time tk, so but it involves also time. The right hand side in the Stratonovich calculus involves also quantities that are evaluated at time tk plus 1, as a result of which every single step of dynamics involves solving an implicit equation. So that's bad from the computational point of view. From the conceptual point of view, the Stratonovich calculus is better for theoretical reasons, because so in theory, Stratonovich calculus is better because the fundamental theory of Stratonovich calculus works exactly like the one of Riemann's or Lebesgue's calculus. So it doesn't bring in new math to be accounted for. So I would say the Ito rule is good for numerics, and the Stratonovich rule is good for theory. It's, if you want to build a qualitative analogy, it's a bit like when you deal with Lagrangian versus Hamiltonian formalism. When you're dealing with Lagrangian's equations of motions, they're very good to solve the theory, because basically they are Newton's equations with whatever geometric constraints you have. But when you want to make theoretical arguments in statistical mechanics, you often rely on the Hamiltonian or the Liouvillean even formalism, because it's theoretical, more sound, more symmetric, more logic, and more easy to deal with for theoretical derivations. So I think these two, this division that I outlined in here is to a large extent questionable. I mean, there's nothing really scientific in what I'm saying. Just say that it's a habit to use the Ito rule rather than the Stratonovich rule when you need to solve, and it's a good thing to use the Stratonovich. It's basically like when you have a convenient gauge choice. You have a gauge transformation, and you work in some gauges when you want to do some calculations. You work in other gauges when you do other things. Which brings me to the question that I was asked. Are the two formulations equivalent from the point of view of physics? So are they equivalent? And the answer to this question is yes, they are, as long as we are dealing with white noise. So what is white noise? White noise is a noise that is a Gaussian, which obeys a commutation relationship, which is the one that we used. And I want to emphasize that the diffusion coefficient that appears here is state independent. Which means Well, again, for the physicist point of view, I don't know, the mathematicians might have a more involved and more rigorous way of dealing with these concepts. Let's stick to the physicist approach. D by dx of d equals 0. It does not depend on configuration. So the diffusion of particles is a constant. That defines a white noise for us in this course, and I think it's a fairly good definition in general. Now, we're going to see in the rest of the course that uh, as long as as we're dealing with systems defined with white noise, which is exactly the system we derived from the Hamiltonian dynamics, then yes, the probability distribution you sample using different stochastic calculus conventions are completely equivalent, which means they lead to probability distributions that obey the same partial differential equations, which we are still yet to derive. And this partial differential equation is called the Fokker-Planck equation. And you can show that you reach the Fokker-Planck equation regardless of the choice of the stochastic calculus you adopt. This is not a proof of this. We will need to derive the Fokker-Planck equations for that. So there will be some kind of an implicit proof of this statement later on in the course for overdamped Langevin dynamics. In the case of colored noise, for instance, noise that depends on x, that's called a colored noise, or a state-dependent noise, then things are very different. So you need to modify your Langevin dynamics in a non-trivial way to make sure that Langevin dynamics defined in different forms of stochastic calculus lead to the same Fokker-Planck equation if the diffusion coefficients explicitly depends on position. Now, this is a surprisingly recent topic of investigation. In fact, I think there is a very few papers that deal with this. And I think the one that I mostly refer of was published in 2000, after 2010 or so. I will probably post this in the description of this video below. But the general case of color noise is far less tricky. I would like to draw some kind of analogy of whatever we are saying with the stochastic calculus. Again, with the gauge invariance in gauge theories. So let me remind you, when you have a gauge theory, there is in principle a whole family of potential fields that lead to the same electric magnetic fields for QED, or chromoelectromagnetic field for QCD, or electroweak. So you have a freedom in going from a potential vector potential formulation to a field formulation of the classical versions of the theory. And therefore you have different Lagrangians formulated in terms of potentials, which lead to the same equations of motions formulated in terms of fields. So, you normally find every mu to be d mu I mu minus d mu I mu. This is outside the statistical field theory course. This is more like a general discussion. And you might remember this from your background in theoretical physics. And you can perform a transformation. Now, this form of the Lagrangian is gauge invariant, which means that you can transform the gauge field according to not to any transformation, the subclass of transformation, and such that the equations of motions, or if you want the Lagrangian, which is proportional to this factor, remains unchanged. In a very similar way, you can have different stochastic calculus leading to the same Fokker-Planck equation, which I now for the first time begin to write in the following form. Oh. We'll derive this object later on in the course. Okay, I think this answers the questions, and I think we're ready to move on to the next lecture. Bye-bye.